Welcome to The Explainer. Today, we are exploring a genuinely fascinating concept, the science of turning massive amounts of everyday industrial waste into cutting-edge, high-performance materials. If you love seeing how innovative, out-of-the-box thinking can solve huge global challenges, well, you're in exactly the right place.
Okay, let's dive into this. I want you to imagine a true circular economy. We're not just talking about recycling plastic bottles into more plastic bottles here. What if the very walls of our homes, the insulation that keeps us warm in the winter and cool in the summer, what if that was actually built using yesterday's industrial garbage? It sounds a little bit like science fiction, right? But as you'll see today, the research shows this is already becoming a hard scientific reality. But to really grasp the solution, we first need to look at the sheer scale of the problem.
Section 1. The Industrial Waste Problem.
Our modern world produces literal mountains of waste. We've got agricultural byproducts coming from everywhere, coffee waste, tea waste, discarded lettuce, citrus peels, and usually this stuff is just tossed out, or at best, it's composted. But the sheer volume is staggering. And then we have the real heavy hitters, like the massive side streams generated by the global pulp and paper industry. Actually, it's this specific paper waste that serves as the focus of our source material today. Because from that massive stream of paper industry waste emerges a rather unlikely protagonist.
Section 2. Meet the hero, lignin.
That hero is lignin. In nature, lignin is basically the chemical glue that holds wood together and gives plants their rigid structure. Now, when paper mills process wood to extract that soft pulp for paper, they strip the lignin completely away. And this leaves behind a dark, sludgy secondary byproduct known in the industry as black liquor. Now, traditionally, factories just take this black liquor and burn it for basic energy recovery. But structurally, oh man, lignin is a chemically rich material. It's packed with aromatic rings and reactive potential. It is literally begging to be used for something better. But to unlock that potential, we need a bit of chemical alchemy.
Section 3. Chemical alchemy, making polyols.
Now, what's really interesting about this slide is seeing exactly how we transform that raw sludge into a usable building block. Researchers use a process called oxypropylation. Don't let the technical term intimidate you. Just think of it as a very intense mixing bowl. The researchers take the raw lignin, mix it with a chemical called propylene oxide, and toss in a potassium hydroxide catalyst. Put all of that under high heat and pressure, and a chemical reaction occurs that grafts brand new chemical branches right onto the lignin molecule. The result? We transform the waste into bio-based liquid polyols, and polyols are the absolutely essential precursor liquids you need to make polyurethane foam. But, not all lignin is created equal. On one side, we have isolated lignin, which is pulled straight out of that black liquor. It's bulky, it has a high molecular weight, and frankly, it has fewer available spots for chemicals to attach. But on the other side, we have depolymerized lignin. This stuff has been put through an oxidation process that literally fragments the molecules. It breaks those bulky structures down into much shorter chains. And what this means is a higher hydroxyl index, which is just a fancy way of saying there are far more reactive sites available for our chemical alchemy. Breaking the lignin down makes it incredibly effective for creating high-quality foams. Section 4. Baking the biofoam.
So we have our bio-based polyol liquid. How do we get from a puddle of liquid to solid insulation? I actually love to frame this dense chemistry as a highly relatable baking process. In the lab, they call it the one-shot free-rise method. And honestly, it's exactly like baking a cake. Step 1. You take your 100% lignin-based polyol and mix it with your basic ingredients, a little glycerol, some water, and a blowing agent, which acts exactly like baking powder. Step 2. You add the binding agent, called dialcyanogate, and mix it furiously for exactly 10 seconds. Step 3. You stop stirring, step back, and let the chemical reaction generate gas, causing the foam to freely rise and cure right in front of your eyes. During this literal baking process in the lab, the liquid mixture rapidly expands inside the synthesis reactor. As it hardens, it's trapping thousands of tiny pockets of gas inside its structure. And those trapped pockets of gas are exactly what make foam such a fantastic thermal insulator. And this brilliantly illustrates what happens next. The final result is a cured, spongy block of biofoam, which you can see on the left. But when we look under a scanning electron microscope, we see the real cellular magic. These closed cell structures reveal something incredible. When researchers increased the amount of lignin in its formulation, the cells actually became smaller and more uniform. And a more homogeneous cellular structure like that traps heat much, much more effectively. Let's look at the hard numbers. When it comes to insulation, lower thermal conductivity is exactly what you want. It means heat struggles to pass through the material. Our standard commercial reference foam on the top row sits at 41.1 milliwatts per meter Kelvin. Now look at the lignin-based foams below it. The formulation with a 20/80 lignin ratio dropped that conductivity down to 37.2. Even at higher densities, the lignin foams performed just as well as, or honestly better than, the petroleum-based commercial standard. This proves a huge point. We absolutely aren't sacrificing quality to be green.
Section 5. The ultimate fire test.
But look, insulation doesn't just need to keep a house warm, right? It needs to keep it safe. So the crucial point is this surprising plot twist regarding biomaterials in fire. Standard polyurethane foam is notoriously flammable. When it gets hot, it degrades rapidly and burns right up. So you might logically assume that stuffing our walls full of biofoam made from wood pulp would be a massive fire hazard. But it's exactly the opposite. Lignin has a built-in fire retardant property. When exposed to extreme heat, its unique aromatic chemical structure decomposes and actually forms a thick, protective carbonaceous char coat. This charring layer acts like a physical shield, starving the fire of oxygen and drastically slowing down combustion. Check out this graph. A thermogravimetric analysis tracks weight loss as temperatures soar all the way up to 700 degrees Celsius. Looking above 600 degrees, that is where the lignin char layer truly shines. It maintains thermal stability long after standard commercial foams have completely degraded. The data shows that the more lignin they added, the higher the thermal stability was under extreme heat. Which leads us to this massive takeaway straight from the researchers themselves. It's totally viable to replace 100% of the commercial polyols in our foams with this paper waste derivative. Think about that. Not 10%, not 50%, but 100%. And in doing so, we aren't just making the insulation greener, we are actually making it inherently safer against fire. So we've followed the entire journey from literal industrial sludge through complex chemical alchemy, down into microscopic thermal cells, and finally out to a fire-resistant building material of the future. It really makes you pause and rethink the whole concept of garbage, doesn't it? Could the key to building the safer, greener, more efficient cities of tomorrow already be sitting right there in our industrial waste bins? It's a fantastic question, and the science definitely says yes. Thank you so much for joining me on this explainer. Keep questioning the world around you, and as always, keep learning.